Good morning, ladies and gentlemen. May I have your attention, please? Thanks. Let's go ahead and get going with our Bellwork today. So in general, we can find the curved length of a segment of a function now using our formula for arc length, where L, right, is given by a definite integral. So as we continue with our modeling and applications, unit 5, right, another application of the definite integral is to find arc length. So what formula would I use in order to find arc length if I'm talking about a portion of the graph f of x over an interval a to b? What would that look like? Kobe?
The integral from a to b of the square root of 1 plus f prime of x squared dx.
Awesome. Thank you very much. Raise your hand if you have the same formula in general. Great. However, we do have an important requirement. Our function f has to be what we call smooth. So we need our function f to be continuous and differentiable on that interval a to b in order to apply this formula. All right, let's go ahead and use it then to find the curved length of a portion of a function f of x. First, let's consider the function f given by sine of x minus x cosine x. We'll graph it first, and then we'll find the length of that function over the specified interval. So let's go ahead and get a picture with our emulator. I want to make sure that we're in the proper mode. Radian it is, good job, and so we'll go ahead and enter our sine of x minus x cosine x, and happy hands. Yeah, take it easy there. All right, and we want to get a good picture along the window 0 to pi, and so I'll probably go negative pi over 2 to maybe I'll go 3 pi over 2. And for my y, maybe I'll go negative 2 to 2 and see how that looks. So we went from 0 to pi, so here comes my function from 0, and we did, oh, looks like I can't see very well. So I'm going to go ahead and change my window now. And I want 0 to pi, and I did, what did I do? Pi over 2. I'm going to make my scales like pi over 4. There we go. And my y max, I'm going to do is 6. All right, let's try that. Okay, so that's a much better picture. We're looking for the length of that curved function over the interval 0 to pi. So for us, if I went by pi over 4, then this would be 0, pi over 2 would be here, right? And pi would be here, so we're talking about this portion of the graph from 0 to pi, is that right? And I have to figure out the length of that. Well, is my function a smooth function, that is its first derivative, right, is continuous over the course of that interval? Quite a picture. Yeah, absolutely. We can see how my function is nice, smooth, and well behaved. We can calculate its derivative analytically and see, right, if it is in fact continuous itself, and then we can set up our definite interval. And so if f is given by sine of x minus x cosine x, then f prime, that is the derivative of x, must be given by what? So what would f prime be given by then? Danny?
Cosine of x plus and minus cosine of x plus x.
Danny, what's the product rule? So the derivative of a product of two functions is the derivative of the first times the second plus the first times the derivative of the second. And Danny knows that cosine differentiates to the opposite of sine of x, but since we had a negative out front, a negative times a negative through the quantity gives me a positive end result. Yes? Yes? I'm all about the math 9, baby. So let's set up our definite integral, and we'll go ahead and math 9 over that interval. I know my length L then, in green, is given by exactly my integral from 0 to pi of the square root of, Kobe told us, 1 plus, and now I need f prime of x squared dx. So inside my f of x, f prime of x rather, I need that whole span. Oh, hey, does cosine x minus cosine x just cancel? Hey, so I just get x sine of x? That's cool. Alright, so I'm going to go ahead and go math 9. That's the exact length, and I'll get an approximation now using math 9 correctly to replace past the decimal. So let's go ahead and do home screen, math 9, the integral from 0 to pi of the square root of 1 plus quantity x sine of x, close angle, close quantity, squared, close radical, with respect to x. Let's see, how many times did I mess up, make a syntax error there? Okay, okay, pinch of salt. Voila! Raise your hand if you had 4.698. Anybody else get that? Hey, if you guys got it, and I got it, well, that's good news then. So it looks like it's approximated by about 4.698 units long. That's pretty sweet. Awesome. All right, let's go ahead and take a look at our third question. For our third question, we wanted to consider f given by a quantity x minus 2 all to the 2/3 plus 3 over the interval 1 to 3. And as I looked at this picture, I got x minus 2 quantity to the 2/3. Make sure you're using parentheses on your exponent or up in there, I guess. With our pretty print, we don't have to worry about it as much as the 83s. And 1 to 3. So I'm going to go ahead and do maybe negative 2 to 5. We'll see what we can see here. So we're just talking about this little portion there. So I'm going to go ahead and shrink my window a little bit. I'm going to go from negative 1 maybe to 6. Let's try that. I have an axis. I have an axis over there just waiting for us to use. And, gosh, I'm kind of picky on it. I don't want all that wasted space. Yes, it's good to be picky though. I'm going to go negative 2 to 7. Third time is the charm. Gosh, that's a good looking picture. So we want from negative 1. We want from negative 1 until 3. And humor me for a minute, if you will. Just gonna get rid of that. If we were, right, to set up a definite integral and try to calculate that, I wonder if I can. No. I wanted to see what happened. So if we did f prime of x and went from 1 to 3 and got this green portion of the graph, okay, I would use the derivative of f. That would be given by power rule, exponent times the base raised to 1 less, times root of the base, and so isn't that just 2/3 quantity x minus 2 to the negative 1/3? And that's the same as 2 over 3 cube root of x minus 2. Depending upon how you'd like to write that. Alright, so if I were to blindly proceed with my length given by the definite integral from 1 to 3 of square root of 1 plus f prime of x squared, so that would be 2 over 3 cube root of x minus 2 closed fraction squared, closed radical dx. The reason I'm doing this is because I want to see what happens with my calculator when I do this. So I'm doing Math 9, my favorite calculator application, 1 to 3 square root of 1 plus quantity, oh boy, 2 over quantity, again, 3, Math 4, is cube root of x minus 2 closed denominator, closed fraction squared, get out of the radical with respect to x. This time I need 2 pinches of salt, 1 for each hand. And, sorry, I got near. So all that was so that I could, right, have a mini freak out sitting. That was like mini freak out. That wasn't the Mr. Fritz freak out that you guys have been waiting for all first semester, now into the second. That was just a mini freak out. So the point of this problem was, what is going on? Why am I getting an error in my calculator? So what's wrong with this? We worked so hard to develop a formula for arc length, right? What's going on here? Vivian? Yeah, my function, right? My function is not what we call a smooth curve, where its derivative, the derivative of that function is continuous throughout. We see that my slopes, right? We've got this cusp where my slopes become infinite as x approaches 2 from the left-hand side. My derivative values, right, are becoming infinite, negative infinity as a matter of fact. But as x approaches 2 from the right-hand side of my original function, my derivative values f prime are approaching positive infinity. And so where we've got that, right, abrupt change in direction in general we call it a corner. More specifically, if our slopes are infinite there and switching from negative infinity to positive infinity, we've got a cusp. My function's not differentiable. And yet, it's continuous. In fact, that point, right, exists and is what? Where the cusp is, what point is that? 2 comma, what point? 2 comma 3, and so we've got a point here. I'm feeling like, I don't know, we should be able to figure out this length, right? And so we've got a couple options at our disposal. Earlier in the year, you guys already had some experience with breaking up, right, a definite integral. If we were to break up this into 2 separate segments, however, on one side, we'd still have slopes that become infinite, yes? My derivative values as x approaches 2 are still going to be becoming infinite whether I break it up at x equals 2 or not. But we can do something else, right? If we were to find the inverse of our function, instead of write this as y equals f of x, what if we were to make this x equals f of y? And then, as my slopes become infinite with respect to x, instead of having infinite slopes that are vertical tangents, now at that breaking point, if I were to rewrite the inverse, I wouldn't have vertical tangents, I'd have what kind of tangents? Horizontal tangents at that cusp point. Horizontal tangents, right? Do those cause a problem in our derivative? No, they equal 0. And so this is a nice tool, right? If I had a problem with differentiability because of vertical tangents, I could try to rewrite x as a function of y, and that inverse then will create horizontal tangents at my problem of concern, which are differentiable. And now I would have no problem. Kobe.
Could you break it into 2 integrals, like from 1 to 2 and then 2 to 3?
That's what I did. I did that numerically. And it gave me slightly different than when I rewrote it in terms of y, based on your grapher. So your grapher uses different approximation methods to get that arc length, and depending upon where it grabs your isolated points from for its Riemann sum, depending upon where it grabs it, it may or may not make a different decimal than my calculator, and so on and so forth. And I think it has to do with your window also. But the problem with that, and the reason I'm thinking that I got different decimals, was because we still have an infinite slope as we approach that 2 from the left-hand side, right? And depending upon how close your calculator grabs values to that infinite slope, may or may not cause a problem, but that point is included in our interval, you know what I'm saying? And so I did do it that way, and I got a slightly different decimal. So what I did was, well, I know that I have no problem if my slopes become horizontal at that turning point, as opposed to becoming vertically, and I got a different decimal slightly. It was like the 4th or 5th place, but that's still sizable when you consider our approximation goes to 9 on our calculator, and so I think it's one of the limitations of our grapher. Another one that jumps to mind that's really easy is like absolute value of x. If you do n deriv, the calculation of the derivative at the corner, the corner of absolute value of x, it'll give you 0. Right? Because of the way it grabs points on either side and does symmetric difference quotient, right? Is the value of the derivative of the absolute value function at the corner equal to 0? Clearly not. It's undefined and does not exist. And so, again, it's a limitation of our calculator. So the way that I got around that, Kobe, to be safe, because I did exactly that. I just broke it up like an improper integral. I got a slightly different decimal. So let's go ahead and see. And then let's compare. So I made another space for you. How come? Well, because we're going to, instead of having this f of x, let's have it y equals quantity x minus 2 to the 2/3 closed quantity plus 3. Let's go ahead and rewrite this as a function of y. So what would we do here? Well, we simply subtract over our 3. Undo the power. How would we undo that exponent? Right? What do we do algebraically to undo an exponent? Yeah, we would do the reciprocal exponent. We could raise both sides to the reciprocal exponent. That would get rid of our exponent. So y minus 3 to the 3/2 will equal quantity x minus 2. And then we can finish it out by adding 2 to both sides. So I'm getting x equals quantity y minus 3 to the 3/2 plus 2. Again, how does this help me? Why are we doing this? Because now at that corner or cusp, right, that I had when y was a function of x, my tangents become vertical. Now at y equals 3, right? We'll see what my exponent. Was I talking? That's always a danger. 3/2. Now let's see what happens to my derivative values, my slope values as y gets closer to 3. I no longer have that that vertical tangent issue. So what do I need? I need dx dy. That is the derivative of x with respect to y. It's not going to work for me. And that would be given by exponent times the base raised to 1 less times the derivative of the base. So I'm just getting 3/2. Y minus 3 to the, now I get 3/2 minus 1 is 1/2, right? Am I going to get a 0 on the bottom of a fraction? No. This is still a positive exponent. It's still on top. So in general, this equals 3 root y minus 3 all over 2. As y approaches 3, is my derivative undefined? No. Is my slope vertical? No. What is the value of my derivative as y approaches 3? 0. Does that exist? Yep, that exists, so I have no problem. So I've basically got around the problem of having a vertical tangent. Now I can use my same formula, but I won't be integrating from 1 to 3, right? I won't be integrating from 1 to 3. I'll be integrating from, well, if y equals x minus 2 to the 2/3 plus 3, then when x equals 1, I get 1 minus 2 is negative 1. Negative 1 to the 2/3 is 1, plus 3 is 4 for my corresponding y value. When x equals 3, I get 3 minus 2 is 1. 1 to the 2/3 is 1, plus 3 is 4 again. Uh-oh, I've got problems. What kind of interval is 4 to 4? That was my x, right? That was my x function. Well, I'm going from here to here. When I rewrite this as a function of y, right? Look at those corresponding y coordinates are the point 1 comma 4 and the point 3 comma 4. So what do? I can't integrate from 4 to 4. What would I get? Well, we can't keep it at any change from 4 to 4. So we're just out of luck. We've taken the time to rewrite this as a function of x. Well, no, this is still my function y equals f of x. Consider what the inverse would look like. So the inverse would look like a mirror image about the line y equals x. So now we'd be dealing with something like, oh gosh, can I do it? I'm hesitant. Can I do it?
I don't know.
I'm going to try. Alright, so I'm approaching this horizontal tangent now. So I'll be okay. Now, Colby, we get to break up because I still have, look at, that's still like a corner kink or cusp looking, isn't it? But now I can break it up, and when I break it up, my tangents are becoming horizontal, they're not becoming vertical, and so I'm not worried about it. The implications of having a non-differentiable function. All right, so let's do it. So where am I going to integrate from? I'm going to integrate from 3 to 4, and then double it. See what I'm saying? I'm going to go from 3 to 4 and double it. So I'm going from 1 unit to 1 unit. Is that going to work? Well, so long as I get this quantity. So long as I make sure this is 3. So how would I get this point? I plug in. How do I get this point? Oh, how do I get this point? Sorry. So I plug in 3, 0, 2, so 2, 3. So this is 2, 3. What's that?
Square root of 0.
Plus 2 is 2, is the x coordinate. So isn't it 2, 3? And this was versus 3, 2. No, this is 2, 3. Ah, so this is 3, 2. All right. So what am I going to do then? What am I trying to figure out from? We need to go from here to here, right? And then again here to here. Oh, gosh darn it. So what are we going to do? Still think 3 to 4 and double it. 3 to 4 and double it. So here we go. After long last, we have now taken the time to rewrite this as x equals a function of y, also that we can figure out the arc length and have a horizontal tangent instead of a vertical tangent. So I'm going to do 2 times the integral from 3 to 4 of square root of 1 plus, and now it's going to be dx dy quantity squared. What's that? Well, that is 3 root y minus 3 all over 2 quantity squared. Let's do it. dy. Oh, okay. All right, let's try it. So we're going to do math 9. And, oh, can I do 2 times that? Oh, can't. Did I orient that? Did I work hard to orient that? I don't want 29. Why did I orient that? Ask myself. Do I have to do the slide? If you don't do the slide, it doesn't work, or what?
No.
I couldn't tell you.
Did you slide too? Does that help? All right. Gosh darn it. I'm ready. Hey! What do we want? 3 to 4. We're going to double it. I'm going for it. And we want square root of 1 plus quantity 3 root y minus 3 close radical close radical over 2 close fraction squared out of radical dx. That's dy, but it's dx. Okay, do we get everybody? Tell me 2.8794. All right, so I did this yesterday twice. And did you do it with x's splitting it? No? All right. I did it with Texas putting it too. I don't remember. But I gotta say, that that's a pretty cool trick to get around the problem of a vertical tangent. All right. So, what do I want you guys to take away from this? Well, I want you to take away that my function must be differentiable, right, over the course. I can't just integrate from A to B if my function is not differentiable. Danny?
I did it twice. I did it once where I split up the x's, and then once where I, like the second time the way that we just did it.
Yeah.
And I got 2.879 the first time when I split up the and I got 2.816 or 8.
I got 2.817 as well.
Yeah.
Yeah. So what's up? I mean, that's a big difference, right?
Yeah.
So,
And then you just got.
so I got 2.879413 when I did it with x's split up at the cusp. And here I got 2.879419747. You know what I'm saying? But like, we shouldn't be getting that big a difference. Like, you're thinking that's a small difference. We still got the correct in 3 places, but what's going on? Well, because your calculator is different than my calculator, right? In terms of where it's grabbing those points from, so we get different results. Slightly, but it's still different, and it should be different. It should get the same approximation to 9 is what I'm saying, whether we do it with respect to x or with respect to y, if everything's on the up and up, you know what I'm saying?
Yeah.
And so, I find that interesting. I find that intriguing. So I thought it was worth just incorporating into our discussion because I thought that was pretty interesting. But I know that rewriting it as a function of y so that my tangents are becoming horizontal, where the derivative is defined, is the way to be sure we're getting it correct, as opposed to breaking up where my tangent is vertical, where the derivative is undefined. That's the danger zone. And that's what I was after with that. But it's kind of interesting. Oh, but enough about me. Seriously. Let's go ahead and take care of our housekeeping. I'll pause this bad boy. Our discussion. All right. So we've seen that definite integrals, right, provide us with a variety of applications in the real world. Today we're going to remind you about how we can use definite integrals in the context of particle motion with position, velocity, acceleration. We'll also look at some consumption, right? If we integrate a rate of change over an interval, the result gives us the net change in that quantity. And then lastly, a little bit of density. And so we're going to be working again with applications of definite integrals today for the first half, and then Friday for the first half, and then test on Tuesday. Let's get cracking. So given a particle's velocity function, can we determine when the particle is at rest, moving to the right, moving to the left, before determining the particle's displacement and distance traveled over the specified interval? Absolutely. And we're going to do it 2 different ways as we continue, right, to marry non-calculator with calculator-allowed methods in accordance with the AP curriculum. So here we go. First up, non-calculator. Yes, we can determine when the particle is at rest. That's code for, I'm going to absolutely freak out. I'm going to absolutely freak out. That's code for stop, velocity equals 0, right? And so we can set this equal to 0 solve to figure out when the particle is at rest.
Feeling the surface freaking out. Thank you. But maybe we should orientate it really bad. Anyway, so like on the top. Yeah. Wait, that's actually super
I think it
fun.
might be better than me painstakingly doing it slowly. All right, so after setting my velocity equal to 0 and solving, we can determine when the particle's at rest, because at rest just means its velocity is 0, it's stopped. And so I'll go ahead and set that equal to 0 and solve, diagonal side by 6, gives me the sine of 3t equals 0. And when would this happen? Well, analytically, I need to know when my sine function equals 0. I also need to take into account my period change. You see that speed factor? That speed factor of 3 means that this particular Ferris wheel is spinning 3 times as fast. So I would need to consider more than once around. I'd have to go 3 times around the inner circle, technically, to get all my places. However, here I'm only going to pi over 2, and so it's not going to end up mapping. In any case, this would happen when 3t equals what? Well, sine is 0, right? When the angle input equals 0 or pi, yes? And so if my angle input 3t were equal to 0 or pi, right, then that would be true. However, this particular sine function is spinning 3 times as fast, and so it's going to spin 3 times around the unit circle in the course of a regular period, 0 to 2 pi as my original. So what I'm going to do to be safe is extend this for another 2 rotations. And so it happened again at 2 pi, would happen again at 3 pi, would happen again at 4 pi, and so on and so forth. As I continue listing these values, however, I see that upon division by 3 to solve for t, pi over 3 falls within my interval, but 2 pi over 3, is that in my interval 0 pi over 2? No, it's past. And so I can stop listing my angle inputs now, because my interval cut off at pi over 3, the last one that will yield me a value that's in my interval is the pi. So what does that happen when t equals 0 and when t equals pi over 3? The next one, 2 pi over 3, is outside of my interval. All right, so we know the particle is at rest when t equals 0. It's at rest when t equals 0 and pi over 3. All right, when is it moving to the right? This sounds like a job for velocity number line. So I'll go ahead and make my number line. Label it v of t and choose the time value. Critical value is 0 was on the endpoint of an interval, and pi over 3. So in between 0 and pi over 3, right, I could choose a convenient, a convenient t value. And so how about pi over 6? Yes? At pi over 6, my velocity function gets 3 pi over 6 is pi over 2. The sine of pi over 2 is 1 times 6 is positive. And so it looks like my velocity is positive on the interval time t equals 0 to pi over 3. My interval stops at pi over 2. However, is pi over 2 a critical value? No, and so what I'm going to do is I'm going to use pi over 2 to get the sine on this interval, because I know that I won't have a chance of changing sine until I would get to this next critical value, 2 pi over 3. So I'm going to use pi over 2 because that's easy to evaluate. 3 pi over 2 then produces a sine value of -1 times the 6 is negative. So it looks like my particle is moving to the right on the first time interval. And your text lists this with inequality notation. So they said inequality notation 0 to t to pi over 3. And moving to the left on pi over 3 to t pi over 2. They took into account the fact that your pi over 2 again wasn't a critical value, so they did include that. They included that as a the endpoint of the interval. I'm just going to leave it strictly because it's the endpoint of the interval to be safe. Right. I know you're upset, but you don't have to start throwing things. Right, we already orange the board 3 times. You have to. We can make it 4, but no, it's doing okay. All right, so now what we're going to do, we'll finish out with displacement versus distance travel. Recall that my displacement is given, right, by my integral of velocity over my integral a to b, which would give me the ending position minus the starting position. That, by definition, is displacement. And so to get my displacement is easy cheesy. If I have the velocity function, I know the difference between my ending position and my starting position is displacement, right? That would be given by the integral of my velocity function from A to B, in this case, 0 to pi over 2. And while I'm at it, let's just go right to it, shall we? 6 sine 3t. Awesome. So can I evaluate this analytically without Math 9? Yeah, we can. We just need to provide for the derivative of my angle, and I know that sine will integrate to opposite cosine function. So 6 out front, provide for the derivative of the angle, 3 by 1/3, so 6/3 is 2. I'm getting negative 2 cosine of 3t.
She's retarded.
Are you okay?
Like started coming in and she like stopped like right in front of the window and she ran away, like literally.
Okay. From 0 to 5 to 10. All right, can I evaluate that? Certainly. So my position function evaluated at my upper limit. I'll pull out the negative 2. Cosine of 3 pi over 2 is 0 minus cosine of 0 is 1. I'm getting negative 2 times negative 1 is positive 2. So I'm getting a displacement of 2 units. This means that, right? While I may not know where the particle started, I do know that at the end of the interval it is 2 units farther to the right. Yes? Now your homework gives you a starting value, a starting position. So if it gives you a starting position, like the particle's at t equals 0, it's at 7 units to the right, then at the end we say it's at 9, right? If we wanted to do that. All right. Can we do distance traveled? Absolutely. What do we need to add for distance traveled? Well, we need to take into account that we were going to the right on this interval up until pi over 3, and then to the left, so we need to add that 2 net changes together to get the total accumulated distance traveled. And so we'll simply break it up at the pi over 3 and evaluate my position function at each of my critical values and endpoints and compare. Kind of like the dun-dun-dun-dun-dun-dun closed interval method from a long time ago. So we'll go ahead and extend the page one more time. I think we're going to make this. And we will use t and my s of t function, slap my endpoints on, and then in the middle, you guys see that? And evaluate my potential position function s of t. What would be? Call it negative 2 cosine of 3t. Now the reason I keep calling it my potential position function is because we can't nail that down. Technically we have a plus c when we integrated that, right, to get this potential position function. It would have to be pinned down with an initial condition, just like when you solve differential equations, to determine the exact position function. But that's okay. We're just after the total distance traveled. So whether I start at 7 and walk 3 to the right and 1 back to the left, or I start at negative 7 and walk 3 to the right and 1 back, I'm still going to have the same total distance traveled. All right, let's evaluate. 0 in for t. Cosine of 0 is 1 times negative 2 is negative 2. Yes? Pi over 3 in for t. 3 times pi over 3 is pi. Cosine of pi is negative 1 times negative 2 is 2. And pi over 2. Cosine of 3 pi over 2 is 0 times in and 0. So it looks to me like our total distance traveled is from negative 2 to 2 is how far? From 2 to 0 is how far? Guess what? Our total distance traveled is 6 units. We know we went crazy with the go-go gadget arm if we got all that gray space on the side, but it was totally worth it. All right. Now we can go ahead and, was that for me? I did that so that I wouldn't have to do all the gray spaces. That's all right. Let's verify numerically. So numerically, that means we get to use our grapher. We're having the, what is analytically versus numerically mean? So analytically is our strictly pencil and paper methods. Numerically is the built-in capabilities of our grapher. So what do we want to do? Well, we wanted to do our Let's do displacement first. So displacement, right? Versus all, right, change in position counting as a positive contribution is easily attained by the addition of one key feature in my displacement formula. Yes, that's right. If I want the total distance traveled over my interval A to B, what do I need to do? I need to add my absolute value parts. Sometimes displacement and distance traveled are the same, right? Sometimes they're different. We saw how they were just different. All right, let's go ahead and verify numerically. So what was my function? My velocity function was 6 sine 3t. I think I'll just do this. 6 sine 3t close input. Very nice. And I want the displacement from 0 to pi over 2. So I'll math 9 bars. Oh no, I can't do that. I'm in pretty print. We want 0 to all kinds of issues. All kinds of issues today. Second pi over 2. Okay. Bars. Y bars, function y1. Oh, that's good news. Does that look familiar? Yes. Can I just scooch in here and snag that? Can I? I'm gonna go for it. Oh. Oh. Didn't work. That's all right. I'm strong. We'll make it work. There we go. Ah! How do you do? Grinding. Hey! Except ours is better. You guys see? Ours is better. It's all right. We knew that. We knew that already. And so it looks like we're verified in each case. Our displacement was 2 versus our distance travel was 6. How do these findings compare with our earlier results? Very well, because we're awesome. All right. You might notice a whole bunch of space underneath this one. Why is that? Because I made up 2 examples early this morning and I didn't have them picked out yet. And so please don't use the entire page to do this one. We've got 2 more things, and that's why I left space for you. Because I just didn't know which ones I was going to use for the function. All right, so let's go ahead and do the same approach, but now let's extend it to a transcendental function, right? With e, my exponential. So b of t equals e to the sine of t, cosine of t on 0 to 2 pi. Can we answer the same questions? Absolutely. You guys have this, right? Yeah, this, okay. So how do I do this? Easy cheesy. We'll take my original velocity. And set it equal to 0 to determine my critical values, that is, my potential changes in direction values and where my particle is at rest. Okay. Will the first term in this product, e to the sine t and exponential of base e, will that ever equal 0? No, my exponential, right, will never equal 0, but this cosine of t equals 0 on 2 pi. When will that equal 0? Well, on 0 to 2 pi, cosine is equal to 0 at what? Pi over 2 and 3 pi over 2. Good. So we've got t equals pi over 2 and 3 pi over 2. So our particle is at rest at those time values, which again was fancy speak for stopped. Now we'll go ahead and make my velocity v of t number line. We'll put on our critical values on my interval. It looks like pi over 2 and 3 pi over 2 are my critical values. And we'll perform our sign test. So convenient value of my first subinterval, I'll pick pi over 4. The exponential is always positive, so that'll be nice. That'll always be a positive. Cosine of pi over 4 is root 2 over 2 is positive. So I'm getting a positive for this first subinterval. if I pick a convenient time value in between pi over 2 and 3 pi over 2, I'm thinking pi. And if I choose pi, then cosine of pi is negative. So negative times the first exponential positive overall is negative. A convenient x value between 3 pi over 2 and 2 pi would be 7 pi over 4. 7 pi over 4, cosine is positive. So I've got positive, negative, positive. And we could simply translate this into, in the interest of time, can I do this? Right, left, right, and not write the intervals? You're okay? You're okay? Good. Let's do analytically, displacement. So my displacement, I know, will be given by the integral from a to b, that's 0 to 2 pi, of my velocity function. In this case, e to the sine t, cosine t, with respect to time. Can I evaluate that definite integral analytically? Can I do that without math 9? Can I find that integer? Yeah, that cosine t is there. It's our little helper. It's our derivative of the exponent, right? Allowing me to apply the exponential rule. The derivative of an exponential is the exponential itself times the derivative of the exponent. This integrates straight out to e to the sine of t. Don't even have to include a negative, so that's pretty sweet. So e to the sine of t is an antiderivative function evaluated from 0 to 2 pi. So if I first one in all the way, I get knocked down, but I get up again. E to the 0 is just 1. Minus e to the 0 is 1. Uh-oh. Did I make a mistake? I'm getting a displacement of 0. Is that possible? Yeah, it just means your difference between your ending position and your starting position was 0, and that's perfectly all right. Now let's see our distance traveled. Oh, way different. My distance traveled, I'm going to go ahead and consider my closed interval method to compare the changes in position such that all of them are counted as a positive contribution towards my overall distance traveled. So I'll make my t-chart. On my t-chart, what will we put? We'll put t, and we'll put my potential displacement slash position function. We got e to the sine of t. Now that includes a plus c, right? We don't have this position function nailed down, and that's why I keep referring to potential, but we know that the changes in position overall are still going to give us the overall distance traveled. So what do we need on here? We need 0. We need pi over 2. We need 3 pi over 2. And we need 2 pi. Does that do it? All right. Into my position function. E to the sine of 0. Sine of 0 is 0. So e to the 0 is 1. Sine of pi over 2 is 1. E to the first is e. Sine of 3 pi over 2 is negative 1. E to the negative 1 is 1 over e. Sine of 2 pi is 0. E to the 0 is 1. Here we can again clearly see the difference between my starting and ending position is 1 minus 1 is 0. And yet my distance traveled is certainly a positive accumulated change. Check it out. From 1 to e is a difference of e minus 1. From e to 1 over e is the difference of absolute value of that would be e minus 1 over e. And from 1 over e to 1, absolute value of that would be a difference of 1 minus 1 over e. Can we put it all together? Yeah, we're adding all this together. And so I get e plus e is 2e. Minus 1 plus 1 is 0. Hello. Thank you, sir. Minus 1 plus 1 is 0. Negative 1 over e minus another 1 over e is minus 2 over e. All right. So I'm anticipating my distance traveled to be that. I have no idea how much that is. Let's go ahead and compare by getting a decimal approximation and utilizing the built-in capabilities of a grapher. Thank goodness I entered y1 in those because I can pull those up. I'm going to go ahead and put a new function. Our original velocity was e to the sine of t. Close exponent times cosine of t, close angle, and I'll try again. So ready? Here we go. On my home screen, I'm going to see if I can't use this again. So let's see. Can I do that? Yeah, but I want to do displacement first. So I need to change my limit. I'm trying to save time, but I'm just making it harder. Was it 2 pi? 2 pi. That. How do we do? Uh-oh. -7. That doesn't even look close. Oh, yeah, it does. Times 10 to the -14th is 0.00001307. That's your calculator telling you 0. All right, good. All right, so displacement we got verified. Now I'll try and pull that up again. Ah! Victory! Gotta take the little victories, right? 2. Uh, 4.700. 4.701. Uh-oh. All right, so here we go. Our calculator is approximating our displacement. 0. That's good news. Not sure if it's good news or not. It's giving us our distance traveled as 4.701 to correct the tree. All right, what do we need to do? We need moment of truth. What's the decimal approximation for our 2e minus 2 over e? Oh boy. I'm nervous. Are you nervous? Grace, how many pinches do I need this time?
I don't need any.
No? Your choice. Yes! That works. All right. So, we're pretty good. I don't know where I went. All right, guys. Let's close out our discussion with a couple more applications of the definite integrals today, and then we'll get you some work time. So let's suppose the fuel consumption of a diesel motor between weekly maintenance periods. Similar context, I remember a test question we had last time when we were doing the Riemann sums, and we had that diesel motor. Over the course of the week, it had the carbon emissions, and we had to figure out the carbon emissions. This is different. This is saying how much fuel is consumed over the course of a week if the fuel consumption is given by C of T measured in gallons per day. Oftentimes, right, a definite integral represents some accumulated change. The key is making the units work. And so back to our very first day when we introduced the definite integral in AB, right, above all, a definite integral is a product of dependent variable values of my integrated function times the independent variable values, so with respect to variable. I want to figure out how many gallons does the motor consume in a week. My C function is measuring gallons per day. So if I were to do gallons per day multiplied by in a week, my 7 days, would I get a result that makes sense in the context of the problem? Yeah, I get my gallons, which is what we're after. So if my C of T is in green, right, and my independent variable, T, right, dt, is measured in days, then my definite integral should produce the desired result. And that's a key theme that we see again and again in integration. And so the definite integral of a rate of change, right, over an interval gives you the net change in the quantity that the rate measures. And that's a recurring theme in both the AB and the BC curriculum. In any case, let's do it. This is as easy as integrating from what to what for the course of a week. 0 to 7 of C of T. If C of T is already defined, you don't have to write it with 4 plus 0.001 T to the fourth. If it's already defined, you can put C of T and still get full credit on it for your response question. But You have to put the dt, otherwise there goes your full credit. So I'm going to go ahead and do that and see what we get. So I'm going to go ahead and do math 9. C of t was, oh, sorry, I'm used to my classic. C of t is 4 plus 0.001 t to the 4th. Close integrand. How do we do? Hey, did you guys get that? Yes? No? So it looks like 31.361 gallons. Over the course of the week. That's pretty sweet. And you guys fit it? I knew it! Hey! Things are great and you have just enough space. Alright, so now let's suppose that a 2-meter long rod has variable density modeled by the function r of x equals 11 minus 4x grams per meter, where x is the distance from the end of the rod, right, measured from the base of the rod. What's the rod's total mass? Let's do a units check. And so density here is measured in grams per meter, and x is the distance in meters, and so if my independent variable x is meters, then will my product, right, will my product of the integrand function times the independent variable result in a unit that makes sense? Yeah, that would give me grams, right, for mass. And so it looks to me like we just throw up the differentiating thing we can just set up. The base of the rod would be 0 meters away from the base, up until the end of the rod would be how far away? 2 meters away from the base of the rod. The r of x function and the x, where x is distance away. Awesome. I can probably even do this by hand. 11x minus 2x squared. Yes. Ah! Thank you, Kobe. I'm back in my 7 days. All right. 22 minus 4 times 2 is 8. Minus all the way through 0. I'm getting 14. Label? Grams. That's it. So we've seen an assortment of applications of the definite integral, and we'll continue to see some more on Friday's class period. Again, you'll have some review time both today and next class. But let's close it up for today. In general, the definite integral of a rate of change over an interval represents ... Given a particle's velocity v of t, write an expression for each of the following over an interval. And A, of course, is supposed to be displacement, and B is supposed to be distance traveled. So let's go ahead and put that. So displacement. And B will be distance traveled. Okay, ladies and gentlemen, so in general, the definite integral of a rate of change over an interval represents, as I was walking around, I saw several correct responses, all different. It represents the area, right, of a region, or the area underneath the curve, or the volume of a solid, or the displacement, right, of a particle over an interval. In general, that definite integral of a rate of change of a quantity over an interval gives us the net change in that quantity that the rate measures. So it represents the net change in the quantity that the rate measures. If it was the rate of consumption of an engine, right, measured in gasoline, gallons per miles or something, right, then the net change in that gas, right, would be my definite integral of that consumption rate. All right, displacement is given by what expression if we're talking about a velocity function v of t? Riley?
The definite integral from a to b of v of t dt.
Thank you. And what key difference do we have for distance traveled, Sydney?
Absolute value of velocity. Doing the same thing for the parts.
Very good. Absolutely right. Raise your hand if you have the same thing for A and B and below. Yes, you guys, the rest of the time is yours. And I did finish this, and so there's a change for you. I got a space for you.
And